So we're looking at this limit. The limit is y approaches 0 of 2y plus sine 3y over 4y. And what's going to be our first step in solving this one? What do you guys think? Yeah, we're gonna use addition to separate them. Exactly. So we know that if we could get the sine 3y over 4y by itself, we should be able to deal with that using our trig rules, and then the other part of it should be pretty straightforward. So separate this out as to the limit as y approaches 0 of 2y over 4y plus the limit as y approaches 0 of the sine of 3y over 4y. And the left-hand part of it, the y's will cancel out, right? And we'll just have the limit as y approaches 0 of a half, which is just a half because the limit of a constant is a constant. Plus over here, we'll pull out the 1/4 that's in front of that y down there in the denominator. And that gives us sine 3y over y. And what do we need to do from there? What do we need to throw in there? Yep, 3 in the numerator, 3 in the denominator. And the 3 in the numerator will get pulled out. So we got a half plus 3/4 of that limit as y approaches 0 sine 3y over 3y, which is 1, giving us a half plus 3/4 of 1, or 5/4. Everyone good there? Any issues with that? All right. So next we'll move into another one that we're going to want to know what this one is. You should already know what this is, right? From last year, you should have had this one memorized. So what's the limit as x approaches 0 of 1 minus cosine x over x? Yeah, exactly, Nick. It should be 0. And how do we show that that's 0? Because if I try to plug in 0, I end up with 0 over 0, right? It's another indeterminate one. So how do we show that this is equal to 0 without using L'Hopital's rule, since we're pretending you don't know how to do derivatives yet? Yes, Adrian, something like that. Yes, we multiply by 1 plus cosine x, right, Alex? So limit as x approaches 0 of 1 minus cosine x times 1 plus cosine x. Oftentimes when we're working with trig functions, we want to multiply by the conjugate. So what does that turn this into? It gives us the limit as x approaches 0 of 1 minus cosine squared x over x times 1 plus cosine x. And why is it good for us to have that 1 minus cosine squared x in the numerator? Turns into sine squared x, exactly. So we got sine squared x over x times 1 plus cosine x. And from there, how do we simplify that down? Because if I plug in 0 there, it's still 0 over 0. Split it up again, right, Alice? So the limit as x approaches 0 of, let's do sine x over x. And then we'll multiply that by the limit as x approaches 0 of sine x over 1 plus cosine x. And the first part of that we know has to be 1, because that's the limit rule that we already know. And the other piece of it, if we plug in 0, we get 0 over 1 plus cosine of 0, which is 0 over 2. And 1 times 0 is 0. So we want to know that one also, right? That's one we should have memorized. And we might also want to remember that the limit as x approaches 0 of cosine x minus 1 over x is also equal to 0. right, so make sure you know both those. So far, so good. All right. So using that same identity that we just learned, how can we solve this one? The limit as x approaches 0 of 1 minus cosine 10x over x. What do we need to do to the top and the bottom? Multiply them by 10, right? Multiply them each by 10. All right. And the 10 that's in the numerator, we're going to pull out to the front of the limit. And just like with the sine of 5x over 5x that we had before, we can, since these are the same, the argument of the cosine and the denominator are the same, we know that this limit's going to equal 0. We got 10 times 0, which is still just 0. Any issues with that? Everybody good there? All right, let's look at this one. Looks a little more complicated, but it's not really. Why isn't it? Exactly, Nick. These are the values of Pascal's triangle. We need to do a quick review of Pascal's triangle and how that works, or does everybody remember that? How to use the binomial theorem to factor stuff like that. Anybody want a review on that? Yeah, okay, we got one here. So, all right, let me throw an extra page in here. So remembering Pascal's triangle, start with a 1, then the next row is a 1 and a 1, and the outer pieces of it are always 1s. And then the 1 and the 1 make 2. We got another 1 on the outside, and continuing down, it's 1. 1 and 2 makes 3. 2 and 1 is 3, and then a 1 on the outside. We got 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, and so on. As we continue down, these values in Pascal's triangle that we get from adding the terms above it are the coefficients of binomial expansion. So this is a plus b to the 0. A plus b to the 0 power is just 1, right? Anything to the 0 other than 0 to the 0 is just 1. This one, a plus b to the first, well, that's just a plus b. And when we expand that out to a plus b, the coefficients are 1 and 1. If we do a plus b to the second power, we've got a squared plus 2ab plus b squared. The coefficients are 1, 2, and 1. They're always those values from Pascal's triangle. So a plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. And then down here, 1, 4, 6, 4, 1, which is the one we see, is a plus b to the fourth, a to the fourth plus 4a cubed b plus 6 a squared b squared 4ab cubed and b to the fourth. So what we should note on our problem is, though, we alternate back and forth between a positive to a negative to a positive to a negative to a positive term. And so if we want to do, if we do a plus b, then they all become positive. But if we do a minus b in here, then each sign alternates to start with a positive, then a negative, then a positive, then a negative. So up here, if we had a minus b cubed, it'd be a cubed minus 3a squared b plus 3ab squared minus b cubed. And so anytime we see these coefficients that appear in Pascal's triangle, we should be able to factor it using that binomial theorem expansion. So this one, our A is like a 1, and our B is like a cosine x. And we've got coefficients of 1, 4, 6, 4, 1 with alternating signs, which means that this should factor to give us 1 minus cosine x to the 4th power all over x to the 4th. Everybody good with that now? Any questions on that? Okay. So now that they're both being raised, both the numerator and the denominator being raised to the 4th power, we got 1 minus cosine x over x. Put the whole thing up to the 4th power. This is the limit that we already know to be 0. So this ends up being 0 to the 4th, or just 0. Everybody good? Any questions on that? All right, so yeah, just recognize those patterns from Pascal's to factor it out. Yeah, it could also be cosine x minus 1, Ryan, if you wanted to factor it that way. Just going in the opposite direction, right? It's still 1, 4, 6, 4, 1, still alternating signs, so we can make cosine the first term. It doesn't matter. Anytime it's a even power up here, it could go either way, 1 minus cosine or cosine minus 1. So for the odd powers, it would matter. But. All right, let's take a look at another one. It's sine 4y over sine 10y. What do we need to do for this one? I'm not sure what you're saying there, Adrian. You're saying, what are you saying there, Adrian? You wrote x over x question mark, and then you wrote a y. That doesn't make any sense. Okay, multiply by y on the top, on the bottom. Yeah, so we're going to do that. I'm going to separate this out a little bit first, right? Like sine 4y over 1 and 1 over sine 10y. And then, yeah, if we throw a y in down here in the denominator and a y in the numerator, those cancel out. But we also need not just a y in the denominator, we also need a 4y, right? And up here, not just a y, but a 10y. So the y's are good. I put a y in the numerator and a y in the denominator, but put a 10 in the numerator, should probably put a 10 in the denominator. If I put a 4 in the denominator, I should probably put a 4 in the numerator. And then we can pull out the 4/10 that are just sort of in the way there and write this as two different limits. And I can't remember if we talked about it the other day, but x over sine x, its limit as x approaches 0 is also 1. We could get that from that same series of the sandwich theorem that we were working through right before we took the reciprocal. If we'd evaluated the limits on each side, we would have found that they were also 1. And so that limit as x approaches 0 of x over sine x is also 1. So this one is also 1. So really what we've got here is 4/10 or 2/5 times 1, or just 2/5. Everybody good with that? All right, let's look at one more here. If you technically need to separate them into two different limits because we haven't proven that having the two of them together is still one, even though it is, you should still separate them out just to be thorough. But keep in mind that problem, as well as the one we're looking at here, could both be done using L'Hopital's rule. So for some of these, you're probably just going to use L'Hopital's rule. For the ones like a couple of the ones we did yesterday, like sine to the fourth of 3z cubed over 4z to the 12th, you're not going to want to use L'Hopital's rule for that one because taking the derivatives of this over and over again are just going to be a nightmare. But for the simpler ones, you could also just use L'Hopital's. So just keep that in mind. What about this one? Tangent 3x over tangent 4x. Could rewrite those as sines and cosines if we wanted to. Because rewriting them with the cosines don't end up really mattering. Because if I plug 0 into the cosines, I just get 1. So a tangent in the denominator is really a cotangent, and a cotangent would be cosine over sine. So I could rewrite this one as this for now. And the sine 3x over the sine 4x part is just the same as what we were dealing with a minute ago. So if I rewrite this like that, I could separate the cosines into their own limit. And I don't need to separate them out within that limit because if I just plug in 0 to cosine 4x, I get 1. And if I plug it into cosine 3x, I get 1. So this is just 1 over 1 or just 1. So that's all we're looking at there for the cosine piece. But for the sine piece, we'll do what we did before, which is throw in a 3x and a 3 and a 4x and a 4. And pull out the 3/4. And we'll have the limit as x approaches 0 of sine 3x over 3x. And the limit as x approaches 0 of 4x over sine 4x times the 1. And 1, 1, 1, and the 3/4 added or multiplied together just gives you 3/4. We all feel okay about these types of trig limits? Any questions on them? That's the last one of those we're going to do for now. So. All right. So there are 6 different trig limits that I'd like you to make sure you have memorized. I'll write them out here real quick. The limit as x approaches 0 of sine x over x is 1. The limit as x approaches 0 of x over sine x is 1. The limit as x approaches 0 of 1 minus cosine x over x is 0. And the limit as x approaches 0 of cosine x minus 1 over x is also 0. And then we didn't exactly expressly talk about this one, but I'm sure you can figure out why tangent x over x is 1 and x over tangent x is also 1. Because if you rewrite the tangent as sine x over cosine x, you end up with sine x over x times 1 over cosine x, and 1 over cosine x's limit as x approaches 0 is 1, as well as sine x over x's. So tangent x over x and x over tangent x also equal to 1. So make sure you have those 6 memorized. All of them can be done with L'Hopital's rule pretty easily too, but good to just know them so you don't have to worry about doing the extra work. Everybody good? Any questions, any issues? All right. let's start talking about limits at infinity then. So we're looking at f of x equals 1 over x minus 2. And if we think about this as x approaches 2 from the left and x approaches 2 from the right, we end up getting either positive infinity or negative infinity. As we approach 2 from the right, we're going up to positive infinity. And as we approach 2 from the left, we're going down to negative infinity. So the one thing that we want to keep in mind about this is that for a limit to actually exist, it has to be approaching a real number. And since these are both approaching infinity, technically these limits don't exist. And we use infinity or negative infinity. We say that it equals infinity or negative infinity just to indicate what the graph is doing, showing how the graph is behaving at those points or as we approach those points. But technically, if you were sitting on the AP test and one of the options was doesn't exist, that'd be the right answer for these because they technically don't exist. I think we should be pretty familiar with these limits at infinity. So let's take a look at one, like 1 over x minus 4 to the third power. And at the vertical asymptote, where's the vertical asymptote? Vertical asymptote is at x equals 4. Good, Elon. So we should get that just by setting the denominator equal to 0. So we want to look for the limit as x approaches 4 from the left. And we want to look for the limit as x approaches 4 from the right. And we'd also be interested in what's the limit as x approaches 4, the two-sided limit of this. So if we approach from the left-hand side of 4, that means we're plugging in something like 3.99999. And if we plug in 3.99999, when we subtract 4, we're going to get a very small negative number. And if we have a very small negative number and we cube it, that's going to continue to be a very small negative number in the denominator. And if I divide 1 by a very small negative, what do we get? Should get negative infinity. Exactly. But technically, this limit doesn't exist, right? Because the result we got out was negative infinity, and that's not a real number solution. If we're coming from the right-hand side, we've got 1 divided by, let's see, 4.0000001 minus 4 is a very small positive, which we're going to cube, which is still a very small positive, and 1 divided by a very small positive is a very large positive. We get positive infinity there. And we already know that this bottom one doesn't exist, but if these were both either infinity or negative infinity, we could at least say infinity or negative infinity here, but since they're different, we'll just have to go with doesn't exist for the two-sided limit. Any questions on that? All right, what about this one? What's the limit as x approaches 2 from the left of f of x? If we plug in something very, very close to 2 to the left, 1.999, subtract 2, it's a very small positive. I'm sorry, a very small negative. And then when we square it, we end up with a very small positive. And that ends up giving us positive infinity. And as we come from the right-hand side, 2.0000001, if we subtract 2, we have a very small positive. And when we square that, it's still a very small positive. So this time from both sides, we get infinity. And so we can state that the two-sided limit is also infinity. even though we know that technically what? Technically, this does not exist. But on the AP test, especially on a multiple choice, and none of you saw the multiple choice questions last year because of all of the weird AP test stuff, they might show this as infinity, or they might show it as does not exist. So be ready for it to show either one of those this year on the AP test. Everybody good? Any questions? All right. What happens when we put in large values of x to a function like this one, 2 plus 1 over x? If I put in a very large value for x, we end up getting 2 plus 1 over a huge number. 1 over x, right, Nick, approaches 0. So we end up just getting 2. And what does that tell us about the graph of this function 2 plus 1 over x as x goes towards infinity? What does it have? Should have a horizontal asymptote, exactly, at y equals 2, right? And we could graph this and see that that's the case. We'll do that real quick, just because that 2 plus 1 over x, and we can see that as we go out towards infinity here, we have a horizontal asymptote to the right of y equals 2. Okay? Now, if we note to the left, we also have a horizontal asymptote of y equals 2. The way we would show that is how? What would we do to show that it has a horizontal asymptote to the left also? We'd have to do a limit as x approaches negative infinity. So if we wanted to do the limit as x approaches negative infinity of 2 plus 1 over x, we'd see that as we plug in the negative infinity, this 1 over x still approaches 0. So 2 plus 1 over x still approaches 2, and we'd see that this has a horizontal asymptote to the left as well as to the right, and we could state that it has a horizontal asymptote in both directions. We want to remember that if you're asked on the AP test to justify a horizontal asymptote, you need to justify it in both directions, to the right and to the left. Cool. So real quick, we're going to go through the 3 different rules for horizontal asymptotes and prove them using the traditional method that we would use to find the limits as we approach infinity of rational functions, which is taking the highest degree and dividing every term by that highest degree. So why don't you guys start this one out? I help my son with something real fast. I'll be back in a second. All right, I'm back. So if we're looking at the limit as x approaches infinity of 2x squared minus 5 over 3x squared plus x plus 2, the highest degree that we have of any of these terms of this rational function is squared. So we're going to divide every piece of both the numerator and the denominator by x squared. That's effectively like doing nothing. It's effectively like dividing or multiplying by 1. So this becomes a limit as x approaches infinity. The 2x squared over the x squared is just 2. And the minus 5 over the x squared is minus 5 over x squared. And the denominator, we end up with 3 plus 1 over x plus 2 over x squared. And as x goes towards infinity, and also as x goes towards negative infinity, a bunch of this all just goes towards 0, right? The 5 over x squared is 0, 1 over x is 0, 2 over x squared is 0 as we approach infinity or as we approach negative infinity. I'm not going to write them both out, but know that we would technically need to do both of them. All that's left is the 2/3. So we know that this has a horizontal asymptote because we're thinking about infinity and negative infinity. We're having a horizontal asymptote in both directions of y equals 2/3. Everybody good there? And the rule for the horizontal asymptotes that we want to remember is that if the degree of the numerator is the same as the degree of the denominator, all we really have to do to find that asymptote is divide the leading coefficients. And that's because when you divide by the highest degree, everything except for those two values cancels out. Everyone good? Any questions? All right. Let's take a look at this one. We're going to do the same thing. We're going to divide everything by the highest degree. And we're going to do a limit as x approaches infinity and a limit as x approaches negative infinity. I'm just going to write them both here because they're both going to come out the same anytime it's just a regular, straightforward rational function. So what are we dividing them all by? Should be dividing them all by x to the, not x to the third, x to the fourth. Yeah, there we go. X to the fourth, that's our highest exponent, is the fourth power. So 2x squared over x to the fourth is just going to be 2 over x squared and minus 5 over x to the fourth. Down here, it's going to be 3 plus 1 over x cubed plus 2 over x to the fourth. And so as we go towards either positive or negative infinity, any of the ones with x's in the denominators are going towards 0. And this ends up giving us 0 over 3 or just 0. So we have y equals 0, the horizontal asymptote, in both directions. And then the last case, when the degree of the numerator is more than the degree of the denominator, we're still going to divide by the highest degree, but we should see that what happens here, we're going to end up with, when we divide everything by x cubed, we're going to end up with 2 minus 5 over x cubed and 3 over x, 1 over x squared, and 2 over x cubed. And all that's left is a 2 divided by a 0. This doesn't exist, and this has no horizontal asymptotes. So our rule for a degree is higher in the numerator than the denominator is no horizontal asymptotes. And if the degree of the denominator is larger than the degree of the numerator for a rational function, you're going to have a horizontal asymptote of y equals 0 in both directions. All right, I want you guys to take a look at this one, see if you can find the horizontal asymptotes for this function. Take a minute or two and try and figure that out. Then we're going to go through it. Sorry about that. Had to go and deal with my children fighting in the same room while they're trying to be in class. Fun times. So first, we're going to look at a limit as x approaches infinity of this one. And what is 9x squared plus 2 being square rooted very much like? As we go towards infinity, that plus 2 becomes insignificant, and it's pretty much 3x. Really what it is it's the absolute value of 3x, okay, over 4x plus 3. And so as we think about this, if x goes towards infinity, 3x is always positive. So the absolute value of something that is always positive is just that thing that you start with, 3x, over our 4x plus 3. And we know what this limit should be because the degree of the numerator is the same as the degree of the denominator for a rational function. It should just be 3/4. So we end up with y equals 3/4 to the right. But when we look at the limit as x approaches negative infinity of our function f of x, that root 9x squared plus 2, sorry, yeah, Nick and Molly, yeah, that 3 in the denominator as you go towards infinity, yes, that's insignificant. Correct. So as we're looking at going towards negative infinity, we still end up with the same thing to start with. The absolute value, but now 3x is actually a negative number because we're putting in negative values for x here. And so when you take the absolute value of something that's negative, you take the opposite of it. And the opposite of 3x is negative 3x, with the 4x plus 3 in the denominator, giving us negative 3/4. So we have y equals negative 3/4 to the left. Does that make sense to everybody or no? Using the definition of absolute value to either get 3x or negative 3x when we simplify down that absolute value. Let's take a look at the graph of it real quick. It's radical, what is it, 9x squared plus 9x squared plus 2. All over 4x plus 3. And so if we look to the right, it's got an asymptote of y equals 3/4. And to the left, it's got an asymptote of y equals negative 3/4. And we note that it does cross through that asymptote. That asymptote is y equals 3/4 to the right. And we cross through it, but that's fine. You can always cross through a horizontal asymptote as long as you go towards infinity or negative infinity, you're still approaching it. Any questions on that?
Your other donut is on. Your half a donut is on the kitchen table. Huh?
All right, real quick, I want you guys to list out these 4 limits. So figure out what those 4 limits are. So what's the first one? The limit as x approaches infinity of e to the x. Should be infinity, yep. Right, if we're going towards infinity, e to the x, we should know what the graph of e to the x looks like, right? It's just going up towards infinity. What about the limit as x approaches negative infinity of e to the x? That one's 0. What about the limit as x approaches infinity of e to the negative x? That's a lot of zeros people are typing. Another 0. And what about negative infinity for e to the negative x? That one goes back towards infinity. Everybody good there? Okay, so we're going to use these 4 limits to solve some more complicated ones now. So let's look at the limit as x approaches infinity of e to the 6 minus 2x minus 5x squared. So the best way to do this one, to really write it out algebraically, is to say, let's let u equal 6 minus 2x minus 5x squared. So if we let u equal that whole exponent, as x approaches infinity, what does u approach? Should be approaching negative infinity, exactly, Kiana, because the 6 and the minus 2x are kind of insignificant, but we have a negative 5 times infinity squared. Infinity squared is infinity, and the negative in front of it gives us that negative. So we can rewrite this as the limit as u approaches negative infinity of e to the u. And what is that limit equal to? From our previous page, that one should be 0. Everyone good with that? Cool. All right, what about the limit as x approaches negative infinity of e to the x to the 4th minus 2x plus 1? We're going to do the same thing. Make a substitution, let u equal x to the 4th minus 2x plus 1. And as x approaches negative infinity, u is going to approach what? As x is approaching negative infinity, u should approach infinity, because we're taking that negative infinity, and the largest degree we've got is to the 4th power, so the rest of this becomes insignificant, and a negative to the 4th becomes a positive. So this effectively is just the limit as u approaches infinity of e to the u, which should be infinity. Any questions on that? Everybody okay with that? All right. Another one of these, another easy one here. We'll let u equal 2 plus x cubed. And as x goes to negative infinity, u is going to negative infinity as well, because the 2 is insignificant and a negative cubed is still a negative. So we got the limit as u approaches negative infinity of e to the u. And that should be what? Yep, should be 0. Good. Remembering this kind of stuff from last year, getting the hang of it easy enough. All right. The limit as x approaches 0 from the right of e to the 1 over x. So if we let u equal 1 over x, as x approaches 0 from the right, what is u approaching? Should be approaching positive infinity. We want to make sure that we're careful about whether it's positive or negative infinity. Right? If we approach 0 from the right, all of the x values that we plug in are positive. And so this is 1 divided by a very small positive, which is positive infinity. If we were approaching 0 from the left, then this would be 1 over a very small negative, and we'd be approaching negative infinity. So we can rewrite this limit as the limit as u approaches infinity of e to the u, which is infinity. Any issues with that? All right, take a look at a couple more of these. What happens if I plug in infinity to the top one there? I get an infinity term, right? Minus another infinity, plus another infinity, plus 0, minus 0. So infinity minus infinity plus infinity. That's another indeterminate form when we're subtracting one infinity from another. That's an indeterminate. And so what's the right method for solving this limit? Okay, factoring out the e to the 10x, exactly. And the reason why we want to factor out the e to the 10x is it's the highest positive power. And if we factor out the highest positive power from all these other terms, we're going to end up with a bunch of zeros in here and just one either positive or negative infinity to deal with at the end. So we'll take out the e to the 10x. And this one, we end up with a 1, and then we're going to have minus 4. What do we end up with there? Minus 4e to the negative 4x, and then plus 3e to the negative 9x, plus 2e to the negative 12x, and minus 9e to the negative 25x. And now, as we go towards infinity, this first piece here is just an infinity. And here we've got 1 minus a bunch of zeros. So we got infinity times 1. Infinity times a constant is still just a regular old infinity. Everybody good with that? All right. As we go towards negative infinity, the opposite sort of thing happens here. This first one here, e to the 10x, as we go towards negative infinity is 0. So is the e to the 6x and the 3e to the x. But plus 2e to the negative 2x, that's plus infinity. And this one is minus infinity. And so again, that's another indeterminate form, the infinity minus infinity. And so we need to factor out the things that are causing the problem, factor out the things that are giving us infinities. So if we factor out e to the negative 15x from this one, we should get a bunch of zeros or constants inside the parentheses with either an infinity or negative infinity out there in the front. So that's what we'll do. We'll take a look at the limit as x approaches negative infinity. We'll take out e to the negative 15x, which is going to give us e to the 25x. It's going to give us minus 4e to the 21x plus 3e to the 16x. And let's see, what's that? Plus 2e to the 13x and minus 9. And now within here, this e to the negative 15x, as x goes towards negative infinity, what should that be? As x goes to negative infinity of e to the negative 15x, what should we get? Yeah, infinity. Good. And in here, this is going to be 0 minus 0 plus 0 plus 0 minus the 9. And we've got a negative constant times infinity, which should give us negative infinity. Keeping in mind, though, that both these limits technically don't exist because the results we got were infinity and negative infinity. So even though we have an idea of how the graph behaves as we go towards infinity and negative infinity, we still don't have an actual numeric limit. Any questions on that? Everybody okay with that? All right. Do a couple with logarithms here. We're going to do the same sort of steps where we did a U substitution like we did earlier. We're going to have to keep in mind what the graph of the natural log of x looks like as we're doing these. So what does the graph of natural log of x look like? We'll take a look at it on Desmos real quick, just so you guys remind yourselves of it. It's been a while probably. Okay, got it on Desmos. So natural log of x, as we go towards 0 from the right-hand side, we know it goes down to negative infinity. There's nothing to the left of 0 because you can't take the logarithm of something that's negative. And as we go towards infinity, even though it hardly looks like it, the function is going up towards infinity. Very, very slowly, but it still is going up towards infinity. So the substitution that we'll do is we'll let u equal 4x squared plus 5x minus 2, the argument of the natural log. And as x goes towards infinity, where is u going towards? Should also be infinity. Good. So we can rewrite this as the limit as the limit as u approaches infinity of the natural log of u. And as we just looked at on the graph, the natural log graph as we approach infinity increases without bound, albeit slowly, so it goes towards infinity. Everybody good with that one? Okay, what about this one? We're gonna do the same substitution. We're gonna let u equal 4x squared plus 5x minus 2. Now we have x approaching negative infinity though. If x approaches negative infinity, what is u approaching? Yeah, once again, it should be positive infinity. Right, because we got the 4x squared, turns that into a positive. So we're looking at the limit once again. As u approaches infinity of ln u, same thing, just infinity, even though technically it doesn't exist. Everybody good there? All right, do one or two more of these before we call it quits for the day. So the limit as x approaches negative infinity of ln 1 over x to the 4th minus 8x. What should we let u equal? Probably this argument of the natural log. So if u is equal to 1 over x to the 4th minus 8x, and x is approaching negative infinity, what is u approaching? Well, we got to think about this. The denominator of this function, as x goes to negative infinity, is dominated by the 4th power, which turns the negative infinity of x into a positive infinity. So this becomes 1 over infinity. And 1 over infinity. Yep, exactly. Darius should be 0. So u is approaching 0. So we'll rewrite this as a limit as u approaches 0. And approaching 0 from the denominator positive, and the value in my numerator is positive. So we're actually approaching 0 from the right-hand side, which is important because 0 from both sides of u. We can't do that because there's no open interval to the left of 0. But since both the numerator and the denominator must be positive numbers based on the x approaching, and just approach 0 from the right, natural log is going towards negative infinity. Let me try and fix it. Is that better? All right, you guys are all good now? You guys can hear me all right? All right, cool. Do I need to go back through this one, or is everyone okay with that one? All right. How about this one? The limit as x approaches 0 of 3x over the cube root of x plus 8 minus 2. Any thoughts on this one? All right, yep, Shayla, we're going to do a u substitution. What are we going to do a u substitution for? Yeah, Adrian, the cube root, everything inside that cube root, well, the cube root and everything inside of it. So we'll do the cube root of x plus 8, which is going to give us a limit, and it's going to give us a u minus 2 in the denominator. We're going to want to change this x approaching 0 to a u approaching something. So if x is approaching 0, u should be approaching 0 plus 8's cube root, which is 2. So we should have the limit as u approaches 2 of 3x over u minus 2. But we don't really want another x in there, so we're going to have to convert the x in terms of u. So if u is equal to the cube root of x plus 8, then what should x be equal to? It should be u cubed minus 8, right? Everybody good with that substitution there?
Hopefully so. The 3 that's in front of the whole thing here can just go out to the front. So we got 3 times the limit as u approaches 2. And if we plug in 2 to this, we end up with 0 over 0. We end up with indeterminate. So we could use L'Hopital's rule, but we're not going to do that yet. We should just be able to factor that numerator. How do we factor u cubed minus 8? Should be u minus 2, right? It's a difference of cubes. U minus 2 times u squared plus 2u plus 4 all over u minus 2. And now those u minus 2's will cancel out. And we've got 3 times, we'll plug in the 2 to the rest of this. That's 4 plus 4 plus 4 should give us 36. Any issues with that one? All right, what about this one? First thing we should do is what? What should we do first? Plug in that 1, right? What do we get? 0 over 0. So we got to find something else to do with it. Probably need to do a substitution here. Okay, we're going to sub out the x to the 1/8. So we're going to let u equal x to the 1/8. So that's going to give us a limit as if x is approaching 1, what's u going to be approaching? X to the, or 1 to the 1/8, which is still just 1. And if u is x to the 1/8, that's going to give us a u minus 1 in the numerator. But we still need to figure out what x is. So if u is x to the 1/8, x should be equal to u to the 8th power. So we've got u minus 1 over u to the 8th minus 1. And again, if we plug in the u as a 1, this becomes just 0 over 0 still. So we have to use factoring to solve this. We'll end up with the limit as u approaches 1 of u minus 1, and u to the 8th minus 1 is a difference of squares, so u to the 4th plus 1 times u to the 4th minus 1. And the u to the 4th minus 1 is a difference of squares, u squared plus 1 times u squared minus 1, which is a difference of squares, u plus 1 times u minus 1. Everybody good with that factoring? Cancel out the u minus 1s, and we've got 1 over 2 times 2 times 2. We end up with an 8. Any issues there? Or everyone good with that? All right, last one for the day. I think we only got 3 or 4 minutes left anyway, so we should probably finish up. And we only got 3 minutes. So what's the substitution we should do with this one? Yep, cube root of the x plus 27. Good, Darius. So we're going to let u equal the cube root of x plus 27. That means that x is going to equal u cubed minus 27. And as x approaches 0, it means that u is approaching 3, the cube root of 27. And so we'll rewrite this as the limit as u approaches 3 of the cube root of x plus 27 is our u. So we've got a u squared to start with. And then minus 6u and plus 9. And in the denominator, we've got u cubed minus 27 squared. Everybody good with that so far? And now we're just going to factor, we can factor out this numerator, and we can rewrite the denominator by factoring out the u cubed minus 27. So limit as u approaches 3 of u minus 3 squared, and u cubed minus 27 is u minus 3 and u squared plus 3u plus 9, and we're going to square all of that because we have u cubed minus 27 squared. And so that's going to let us cancel out the u minus 3 squared in the numerator with the u minus 3 squared in the denominator, giving us 1 in the numerator, and the denominator, what is that? 3 squared plus 3 times 3 plus 9, all of that squared, which is what, 9 plus 9 plus 9 is 27. And 27 squared ought to be 729. That's 3 to the 6th power, 1 over 729. Any questions or issues with that? All right, that should be it for today.